Dear all, a very good day. In the present lecture, we are going to look at power consumption and chip area for resistive load inverter. In the previous two lectures, we have studied about resistive load inverter, its current equations and working. Thereafter, we have looked at or you can say we have focused on the calculation of its terminal voltages like VIL, VIH and VOL and VOH. In the present video, their power and consumption chip area are going to be of the focus. Okay, so let us start. The average DC power consumption of a resistive load inverter is found by considering the two cases Vin is equal to VOL and Vin is equal to VOH. There are two cases where the inverter is functioning the most. Okay, now when the input voltage is equal to the VOL, the driver transistor is in cut off. Okay, so if our input voltage is VOL, at this time output is VOH and the driver transistor is in cut off region. So there will be no current flow in the driver transistor, and consequently current flow through the resistor will also be or you can say current flow through the load resistor will also be 0. Okay, so consequently there can be only a minute leakage current which can be neglected, and there is no steady state current flow in the circuit. Okay, thus ID will be equal to IR, that is equal to 0, and the DC power dissipated is also equal to 0, neglecting the leakage current. Now when the input voltage is equal to VOH, okay, so in this case if the input voltage is equal to VOH, output will be very low, VOL. Okay, and in this case both the driver transistor and the load resistor conducts a non-zero current. Since the driver is in on state, it may be in saturation or in a linear region, probably in the linear region, so it will conduct, which will result in conduction from the load resistor as well. Okay, and when the input voltage is equal to VOH, on the other hand, both the driver transistor MOSFET and the load resistor conducts a non-zero current. Since the output voltage in this case is equal to VOL, the current drawn from the supply can be found by the simple equation. We have applied KCL across the resistive element, and we know at one end is VDD applied voltage and other end the voltage is VOL. So VDD minus VOL upon RL will be the current flowing through the resistor, and same current will be flowing through the drain terminal of the MOSFET. Okay, now we can assume that the input voltage is low during 50% of the operation time and high during the 50% of the time. So the average DC power consumption of an inverter can be estimated as PDC is equal to VDD by 2 into VDD minus VOL upon RL. Okay, so VI is the power. Since now we know that the cycle is open only for 50% of the time. If we are taking transient input voltage, transient cycle where it is on for 50% duty cycle, so we have taken voltage as VDD by 2 and VDD minus VOL upon RL is the current that is flowing. So the chip area occupied by the resistive load inverter circuit depends upon two parameters: W by L ratio of the driver transistor and the value of the resistor load. So at this time the power will be consumed only because of W by L ratio of the driver transistor and value of the load resistor, because current depends upon the W by L value and resistive value of the load resistor. Now the area of the driver transistor can be approximated by the gate area. Okay, now we know that gate length is kept L, and it is the smallest possible value for a given device technology. Okay, the gate area will be proportional to W by L ratio of the transistor. So the resistor area on the other hand depends very strongly on the technology which is being used to fabricate the resistor on chip. Okay, so W by L can be precisely controlled because of the gate area and whatever device technology we are using. However, the resistance value of the resistor depends greatly on the type of resistor which is being fabricated. Now resistors are basically fabricated by two methodologies. Okay. And these are diffuse resistor and polysilicon or undoped resistor. Now, what is a diffuse resistor technology? Diffuse resistor is fabricated as an isolated n-type or p-type diffusion region in a contact on with a contact on one end each. So it will be a diffusion region of either p-type impurity or a diffusion region of n-type impurity with contacts on both the sides. The resistance is determined by the doping density of the diffusion region and the dimension, it is length and width ratios of the resistor. So how much we have doped a particular type of impurity and the total length which the resistor has been formed, these will dictate the resistive values of the resistor. Now the placement of resistor structure on chip commonly is in serpentine shape, that is it is in the shape of a snake, one layer over another, one layer then second layer, and it will be forming continuous S-type structures. Okay, this helps to introduce more resistance in a limited area. Okay. So the placement of the resistors in serpentine resistor structure on the chip is commonly in serpentine shape. For compactness requires significantly more area than the driver MOSFET. Now, cause when the sheet its sheet resistance is discussed now. Okay, cause its sheet resistance ranges between 20 to 100 ohm per square, and hence a large length to width ratio is required. Now sheet resistance values are very less, so if we require a larger values of resistance that we have seen in the previous graphs, if we will calculate the sheet resistance according to the graph value in the lecture discussed in the VTC, we were using 10 kilo ohm resistors. So if our sheet resistance is 20 into 100 ohm per square, you can assume how much it will take the length to calculate to get a 10k resistance. Okay, so therefore there is an alternate approach which can be used by using an undoped polysilicon. Okay, in conventional polysilicon gate MOS technology, polysilicon structure forming the gate of the transistor and the interconnect lines are heavily doped in order to reduce resistivity. Okay, so if we are doping them heavily, the polysilicon structure, they will reduce the resistivity. The sheet resistance of the polysilicon the sheet resistance of the doped polysilicon interconnect and the polysilicon in the gate is about 20 to 40 ohm per square. If the section of polysilicon interconnect are masked off from the doping step, okay, interconnects are masked off from the doping step. On the other hand, the resulting undoped polysilicon layer has a very high sheet resistance in order of 10 mega ohm per square. So easily the required 10k ohm resistance can easily be formed depending upon the doping levels of the polysilicon. The very compact and very high value resistance can be fabricated using undoped polysilicon layer on okay, but the drawback of this approach is that the resistance value cannot be controlled very accurately, which results in large variation in the VTC. Okay, so presently the technology does not hold so good in polysilicon approach because its resistance value is not controlled to a very accurate level. Okay, therefore the voltage transfer characteristics show discrepancy from transistor to transistor. Thus, these resistive load inverters with undoped polysilicon resistor are not commonly used in the logic gate circuit where certain design criteria such as noise margin are expected to be met. So, if we are very stringent on the qualities of the noise margin, then this type of the resistance value is avoided. Okay. Simple inverter structure with large undoped poly load resistor are used primarily in low power static random access memory. Okay, cells where the primary emphasis on reduction of steady state DC power consumption, operation of the memory circuit is not significantly affected by variation in inverter VTC. So if VTC does not have a very significant role in the particular application such as SRAM, then we use polysilicon type load. However, if the VTC plays a very important role in functioning of the circuit, then we will use resistive load inverters or diffuse resistor inverters instead of polysilicon resistors. Thank you.